third and last speaker for today is Konstantinos from the University of Crete, who will talk about mean ergodic theorem along with.
So thank you very much, the organizers, for inviting me here. These past 2 days, we had many talks about Nil spaces and their usefulness in ergodic theory and arithmetic combinatorics. On the other hand, I will take this in very different directions today. And at least for the first half of the talk, I want to talk about results where we absolutely do not want to use Nil space theory or Nil manifolds. So the first half of the talk will be about some recent developments in joint ergodicity. And let us start by just mentioning the general setting that we're working with. We have a standard measure preserving system, and we have some sequences A1 to AK of n, some bounded functions F1 to Fk, and we want to study these multiple averages here for certain classes of sequences. So as we all know, the most important case that we have polynomial sequences was established 15 years ago, approximately. In most cases by Host and Crete, in the general setting by Leibman, using the Host-Crete theory of characteristic factors. So our goal is to establish similar results, but not necessarily for polynomials. We'll consider sequences of polynomial growth, actually sequences that do not grow faster than some polynomial. And we will try to find some information about the mean convergence of these averages. So these are some examples of sequences that we can study. We can consider the integer polynomials, or more generally, real polynomials by just putting the integer part. So we have, for example, real polynomials like n cubed over 3 plus n of square root of 5. We can have fractional polynomials. So these are called fractional powers. I will use them often as examples. And more generally, we can have a smooth function, a well-behaved smooth function that has polynomial growth. We just consider the sequence Fn by just inserting the integer parts. And these are some examples of sequences that we can cover with our results. And generally, we want the function f to be smooth, have polynomial growth. And this does not make much sense, but essentially, we want some monotonicity assumptions. We want some information about the limits of the functions f. So the most important class of these functions that have these properties is called the functions that belong to a Hardy field, which we'll consider now. So before we go there, it is a very interesting problem what happens when sequences do not have polynomial growth. So if they have exponential growth, we know that all results are false, but we do not have many examples for sequences that are good for convergence, even for rotations of the torus. So some equidistribution results that we know for sequences of polynomial growth are not known for faster growing sequences. So we can give a definition of what is a Hardy field function. So essentially, we consider the germs at infinity of real valued functions defined on some half line, and we want to consider a subclass of them that is closed under differentiation. So these have some nice properties. The best example of these functions are the functions that belong to the Hardy field of logarithmic exponential functions. So these are just functions that are made by using the standard operations of addition, and we can include just the functions x and log. A non-example of sequences that we cannot cover are trigonometric sequences. So, for example, the function t sine t is an example that we cannot cover in general. So the Hardy field functions have nice properties. The functions that belong to a Hardy field always have a limit as t goes to infinity. And they are also infinitely differentiable and eventually monotone. So this is used in several parts of the proof. And another very important property is that if I have two functions, f and g, by definition, this is a function in H. Our H is a ring, a field. So this is a function in H. So it has a limit as t goes to infinity. So essentially, this tells us that it makes sense to consider what it means for one function to grow faster than another. So if this limit is infinity, we can just say that f grows faster than g. If it is a constant different from zero, we say they have the same growth. If it is zero, we just say that g grows faster than f. So if we consider general, a more general class of functions, this is not trivial. What happens when we consider this ratio? So let's look. So this was the definition of the Hardy fields, but you should all keep in mind the Hardy field of logarithmic exponential functions, which has the most natural examples of simple sequences that we could construct. And let us see what happens in the simple case when we have single averages. So in this case, when we want to establish mean convergence, we can just use the spectral theorem for operators. So this tells us that this simple correlation sequence is just the Fourier transform of some bounded measure of the torus. So we can write this L2 norm here as some exponential sums of the sequence of the floor parts of A1 of n. So we had a problem for mean convergence, and we turned it into a problem for equidistribution, for calculating exponential sums on the torus. So this is what I'm saying here. We just need some information about the distribution of this sequence. And this was proved by Konstantinos in 1994, who gave necessary and sufficient condition for a function of polynomial growth to be uniformly distributed on the torus. So if the function A stays logarithmically away from rational polynomials, then the function, the fractional parts of the sequence AN are uniformly distributed modulo 1. So, for example, the functions n to the power of c, when c is not an integer, for example, n to 1.5, or the function n log n, we can easily see that they satisfy this condition. So we immediately can deduce that that the sequence of their fractional parts will be uniformly distributed modulo 1. Obviously, for integer polynomials, this condition does not hold. But for polynomials with irrational coefficients, we have the same thing here. So we also get that this is uniformly distributed modulo 1. But the sequence log n does not satisfy this criterion. So this sequence, we can show that it is not uniformly distributed modulo 1. And the main reason is that in very large intervals, this is essentially a constant sequence. So when we try to calculate the averages of these exponential sums, we can show that they do not converge to 0. And an important application of this equidistribution theorem was that if a function A stays logarithmically away from all real multiples of integer polynomials, so here I would need to put the same condition, but this would hold for all polynomials multiplied by some real number C. In this case, we have convergence of the single averages to the correct limit, which is the integral of the function f, at least in ergodic systems. In non-ergodic systems, I will just put the conditional expectation there. So from now on, I will only focus on ergodic systems because we can just do an ergodic decomposition in the case when we have a non-ergodic system. So I will always, when we calculate the limits, I can always put the integral instead of the conditional expectation. So let us return now to the case of multiple averages. So if we consider just rotations on finite dimensional tori, we will see that we need the same equidistribution assumption on the linear combinations of the original function. So if I have two functions, I consider a rotation on the two-dimensional torus, we will see that I need the same condition for linear combinations of the functions A1 and A2. So this condition, we will show, is actually sufficient to establish L2, the L2 convergence in the general case. So what do we mean by that? We're given K functions, A1 to AK, on our Hardy field. They have polynomial growth. And we assume that all linear combinations of these functions, so let's say A is the linear combination of the functions A1 to AK, satisfies the equidistribution assumption in our previous lemma. So it stays logarithmically away from rational polynomials. Then in all ergodic systems, we prove that the limit of the averages is the expected one, the product of the integrals. So this was a conjecture which I found in, I think it was made by Konstantinos 10 years ago, I think. And many cases, many partial cases were established before this theorem. We can take a look at some of them. Konstantinos proved this theorem in the case where our original functions are just fractional powers. But he also assumed that these integers Ci are all distinct. So I cannot have t to n 1.5 f1 and the same t to n to the 1.5 f2. So I need them to be all distinct. And Karagioros and Koutsogiannis established a similar result for linearly independent polynomials over the rationals. So obviously, if we just take rational polynomials, we cannot get our result. We have to apply some total, we have to assume some total ergodicity for our original system. But in this case, we can just consider, we do not have to have any assumptions of total ergodicity. And recently, a result of Bergelson, Moreira, and Richter was established in this direction. So this is just a special case of their theorem. Say you have the functions A1 to AK, and this symbol here denotes the linear combination of the functions A1 to AK and of all their derivatives. So this set is just the linear span of A1 AK, A1 prime to AK prime, A1 2 times prime, etc. And if we assume that all functions here stay logarithmically away from real polynomials. Then they established the theorem that I mentioned above. So they established that under this assumption, these averages here converge to the product of the integrals. So their method was quite different from what we, from the method used in all these results was quite different from what I will show in the proof. So first of all, their method did not necessarily deal with Cesaro averages. They used a different averaging scheme, which can be used to cover some more extreme cases. So I told you that the sequence log, yes? No, I told you in the theorem above that we do not need this assumption. So this is, for Cesaro averages, this is a special case. But I told you before that the sequence log n is not equidistributed for Cesaro averages. But if you take logarithmic averages, for example, then you can show that the sequence log n is uniformly distributed. So if you weaken the averaging scheme, you can still get a convergence result similar to the above. So here, you could have one of these functions to be log n, for example, but if you had logarithmic averages, you would still have a statement like this. And the advantage of that method is that you were able to get some nice multiple recurrence results that we cannot get with this method here. So our method is strictly for Cesaro averages. I do not know of a way we can cover the sequences that grow slower than log n, for example. But a corollary of our theorem, since we know the limit of these averages, we know that they converge to the product of the integrals, we can show a multiple recurrence result in general systems. And using first-inverse correspondence principle, we can also get a density result, a recurrence result on Z. So if you have a set of positive upper density and the functions A1 through AK satisfy the assumptions of our theorem, then you can show that you have many configurations of the form M plus floor A1 of n, etc., M plus floor AK of n. Although this result was established with the method of Bergelson, Moreira, and Richter by a different averaging scheme. And the different averaging scheme can also give you the same for Cesaro averages, but with a lim sup here. So this is just a minor improvement. We just replaced the lim sup with lim inf. But the main point was establishing the convergence of the ergodic averages. So before we go into the proof, let us discuss a bit how the proofs in the past went. So let's say that our sequence A1 to n is just the simple sequence n to 1.5. And even in the simple case of single averages, the idea was to apply the van der Kolk inequality here to reduce the complexity of this sequence like we do for polynomials. So for example, if I apply the van der Kolk inequality once, I will get expressions of this form. So I combine the integer parts here, but ignore that for now. Essentially, you can do that with minor problems. So I also have an average over the shifts here. So the sequence that we have here essentially looks like m times the derivative of a. And the derivative of a is just m times n plus modulo some constants or some error terms. So if we apply the van der Kolk inequality once, we draw the degree of the sequence by one, essentially. So we can use this method for this function. But what do we do when we have the function an? It's just n log n, which was the typical example that we could not do with previous method. If we apply the van der Kolk inequality once, we will essentially get the derivative of the function, which is just log n modulo error. Actually, it's just log n plus 1. And the function log n is bad for the convergence of ergodic averages. So this method breaks down. So usually you have to add some assumptions of the form that your function satisfies the growth condition of this type. Here I mean the big O notation. This means that this grows faster than tk log t, and slower than tk plus 1. You have to add an assumption of this type. And so we need a different approach to cover the general case. So I think this example, if you manage essentially to cover this example, you cover the general case. So, okay, that is an oversimplification, but it is a good baby problem to solve it in this case. For multiple averages, obviously, in the single average case, you just use a spectral theorem. So, thank you. So in order to prove this theorem, remember that our theorem concerned convergence to the expected limit, the product of the integrals. So recently there was a very nice theorem of Tsinas, which characterizes when you have norm convergences to this correct limit. So this notion is called joint ergodicity. We can revise it here. So generally, you have to get some seminal estimates by the post-class seminars, and then this using the structure theorem, this reduces the problem to an equidistribution result on Nil manifold. But when you have convergence to the product of the integrals, you can just skip the second step essentially. So let's first give a definition. The sequences A1 through AN are called jointly ergodic if for any ergodic system, we just have that the L2 limit of this multiple average is just the product of the integral. So joint ergodicity means convergence to the product of the integrals, essentially. So what is this theorem of Tsinas that gives us these nice conditions that we can easily check? So let's give a definition first. Assume again that we have integer sequences A1 through AK. And these are called good for seminal estimates if there exists a positive integer s, so that when one of the functions is orthogonal to zs minus 1, when we have this equality here, then the limit of our averages is just 0. So when one of our functions is orthogonal to one of the postgra, to the appropriate postgra factor, we just have that our limit is 0. And the second definition that we're going to give is that our sequences are called good for equidistribution if for any linear combination of them, these averages of exponential sums converge to 0. So the first condition is just what we typically do when we want to reduce our problem to nil systems. So being good for semi-norm estimates essentially means you can reduce the problem to nil systems. That's essentially what it means. And the joint ergodistic criterion from Tsinas from 2 years ago says that the sequences A1 of AK are jointly ergodic if and only if they are good for semi-norm estimates and equidistribution. And this powerful theorem allows us to skip this second step of establishing convergence on nil manifolds for our original sequences. So, in our problem, we have to check this condition. Now we'll talk about the proof of this. And the equidistribution condition follows easily. Why? Because I assume that the linear combinations of our original functions are essentially far away from polynomials, so they are uniformly distributed. Typically, you have our sequences had the integer parts here. This can be removed by a simple argument. Don't want to spend time proving this. So the main bulk of the proof relies on getting the required semi-norm estimates for our original averages, which was something that we had to do anyway, but we just skipped the second step to prove our theorem. Actually, for semi-norm estimates, we can weaken our assumptions completely. We can weaken our assumptions significantly. Thank you. So if we have this theorem, says that if we have functions A1 to AK that satisfy the following. The first function, A1, grows faster than the logarithm. In addition, the function A1 minus A2, the function A1 minus A3, etc., and the function A1 minus AK must also dominate the logarithm. Then, for any measure preserving system, such that the first function has semi-norm 0, our averages converge to 0. So what we do here is we fix the function f1. We assume that this function has semi-norm 0 for some appropriate s. This s depends only on the original function. And what we want is just the first function to dominate the logarithm, and the functions, the pair, not all the differences, but the differences where the first function is just a1 must dominate the logarithm log. So, for example, the function ak can be anything. It can even be a constant. We don't care. But we want a1 minus ak to dominate the logarithm. And then you get semi-norm estimates with this weaker assumption. So what this gives us is, suppose we have a weak mixing system. So in this case, the first graph factors are trivial. So if we have the previous theorem, assume we have established that. And now assume that we have a weak mixing system. So now we just assume that our functions a1 through ak dominate the logarithm, all of them, not just the first one, like in the previous theorem. And we also assume that the pairwise differences of these functions also dominate the logarithm, not like the previous theorem where the I was always 1. Then for these weak mixing systems, we still get convergence to the product of the integrals. So if we recall our condition on the equidistribution, the condition from the theorem of Besser-Sum, it says that we have two abstractions for equidistribution. You are either a rational polynomial, something periodic, or you are growing very slowly, slower than the logarithm. So if we assume weak mixing, essentially we just throw away the abstraction from the rational polynomials. We only have to deal with the growth condition that u must be faster than the logarithm. So in this case, our theorem generalizes a lot. Yes. That it is weak mixing. Oh, okay. I didn't write it. So sorry, that is on me. The system must be weak mixing for this to hold. Otherwise, it is obviously false. You can just take integer polynomial, and this will be false. Sorry. Our proof, I don't know if it can be carried necessarily to tempered functions, because we assume we essentially need to take derivatives of arbitrarily large order in our proof, and they did not try to optimize how much these derivatives, how big these derivatives need to be. So let's just go to the proof. For integer polynomials, we have the classical patent action scheme that shows us that we can get semi-norm estimates in this case. So this was a theorem from 15 years ago by Lyman, and this in many cases were established by Horst and Crete. And the idea is to our functions, if we use the Taylor expansion, they can be approximated by a real polynomial if we restrict it to very short intervals. So we will work with averages on short intervals. There, we can approximate the function with Taylor polynomials, and then we can apply the induction scheme to establish the semi-norm estimates that we want. The next bullet says that we apply the patent induction scheme that I talked about. And there are, of course, some technical problems here. So if we just do this, it doesn't work. There are some cases where if we have, as I say in the bullet, a fast-growing function and a slow-growing function, as we will see in an example shortly, we have some problems, and we need some additional techniques to overcome this. So let us see an example where this does work. So assume we have these functions, n log n and n to 2/3. And what I did here is, instead of having the average of from 1 to n, I restricted to the average over a short interval. So it is easy to check that if we have that the averages on the short intervals converge to 0 under the assumption that the function f has semi-norm 0, then the longer averages will converge to 0 as well. So the length of the interval doesn't matter that much. I picked it here to make the calculations easier. So if you use the Taylor expansion for this expression, so n is the base point for the interval. The h can go as large as the length of the short interval. If you do the Taylor expansions, you have the quadratic term, the smaller degree terms. I omitted them because they do not matter that much in the induction scheme. And this error term just the residue from Taylor's theorem. And this is O of 1 because we picked the interval appropriately. So if you write down the third term, it's something like h cubed over n squared. But since 8 can only grow approximately like the square root, this, if we do the division, we see that this converges to 0. And with some calculations, you have the same for the second function. We approximate it by a linear polynomial in this case. So if we write this down and do some hand waving to essentially throw away the error terms, we reduce the problem to these averages here. And I do not care about the smaller terms. The only term that matters in this example is this one in the induction scheme. So we have reduced our problem to the case of polynomials, essentially. But this was an example where this works. Let us see an example where this doesn't work. So here I just described what we did, what we saw in the previous example. We just picked a short interval. We approximated by polynomials. And I explained in the second bullet that you cannot do this for this pair of functions. So the problem with this function, the log squared of n, it grows very slowly. So if you try to do the approximation, you can pick anything as a short interval, almost anything. I do not want to explain further about this. When you try to do the approximation, you can only get approximations by a constant polynomial. The linear degree term will always be O, small o of 1. So even if you take your interval to be essentially very large, almost like the length of the parameter n, this will always be the case. This term will always be a constant, and this creates a problem in the induction scheme. We will see how this problem appears in the second example. So this is general happens when I have a fast-growing function. So a fast-growing function means it grows faster than some fractional power. A slow-growing function is something that grows slowly than all fractional powers. So the main examples in this case are just powers of the logarithm. They always grow slower than all fractional powers tough to delta. So in order to combat this, we have a technique, but do not pay attention to this because we will explain it in the. Actually, let's go back to the previous example. So what I wanted to do is we thought that if we saw that this converges to 0 on the short interval, you get the same for the long interval, but you do not need actually to prove something like this. You only need this to happen in an average sense. So essentially, you want this to converge to 0 for almost all n, essentially. So you just put another average here over the capital N. And we claim now that this double average converges to 0 under this assumption. So let's see the second example. This can be proven with an elementary, yes? You mean this one? This is just the Taylor expansion around n. So this is just the second derivative of n log n. It's just the first derivative is essentially log n. The second derivative is essentially 1 over n. So this just appeared here. This is just calculation. It's not. So let's see the second example. So in this example, I have one fast function and one slow function. This grows slower than all fractional powers. This grows faster than all fractional powers, than some fractional power. I picked this one because we had already done the Taylor expansion in the previous example. So I will just copy it here. The second function you can show, as we discussed, that in this short interval, this is just always negligible. So this sequence is essentially constant in this interval. So what you get is this term gives you a polynomial. This was the calculation in the previous slides. And essentially, both of these iterates are the same. You have this iterate here for G, and you have just f to log squared of r. So this here does not vary with h. So if I did not have this double average here, I could essentially get similar estimates for this function that depends on small r, which is not very helpful. But if I put the outside average here, we will see that you can use this after the first phase induction to eliminate this constant function. So we want to bound the inner average using the van der Kolk inequality. So there are two ways, and I will not have time to describe both of them. But first of all, you do this change of variables here. So if you just did van der Kolk blindly here, after you do van der Kolk twice, you essentially get something like you will get the term something like let's say the shifts are M1 and M2. You will get something like M1, M2 over R. And if M1 and M2 do not grow fast enough, this will go to 0. So in order for this coefficient to not go to 0, we do a change of variables here. So if we write h in this form, essentially, instead of having our main term to be this, we can just write it like k squared. And you obviously get smaller order terms, but they will, it turns out that they do not matter for the PET induction scheme. So if you have averages like this, the S does not matter because it's on the smaller terms. You apply the van der Kolk inequality twice. We pick some parameter m, but it is finite. We will keep it finite until the end, where we send the limit after we eliminate the r's. So the van der Kolk inequality gives you an error term like 1 over m and an error term like m over n, m over, sorry, the length of the interval, this one. Since we picked m to be finite, this error term is just something negligible here. So in our case, we did the PET, the van der Kolk inequality twice to bound the inner average over something like this here. Some, let's say, polynomial correlation sequence. So if we return, so I will probably skip this for now. Maybe we can return later. So if we put this bound for the inner average on our double average before, so we had the outer average over the small r. We have the main term from the PET bounds here. And because we picked m to be finite, we can now interchange the limits. So now we essentially keep this constant, and we want to get similar estimates on this average here. So in this example, I will just use the known case from k equals 1 to get the similar estimates quickly. So our main function is this one. We're going to get similar estimates that depend on this function. So on inner average, if we set r, if we send r to infinity and use the kappa equals 1 case, we can get the similar bound from this function here. This depends on M1 and M2. So if we put this bound on the average, on this average, we essentially want similar estimate for this. So obviously, we have some error terms here that depend on capital M, but now we can just send M to infinity. And if we just expand this, we arrive at averages of polynomials in several variables. And these essentially are known to have to be controlled by post-Grass-Seminole. And essentially, this is the final step. We are done with the proof of theorem. How much time do I have? Okay, so let's not talk about the problem of little manifolds. Let me make a comment about the general pet bound. So in general, you have sequences that depend on R. So because our example was very simple, actually, when we did this change of variables, obviously our coefficient, this coefficient here, is just a constant. It turns out that the leading coefficient of this polynomial is actually very important in this proof. And for example, if you had a coefficient that depends on R and you apply the pet bound, then modulo some modifications, you get a bound like this. And in the general case, you get similar polynomial expressions that have some weird cubic structure. So they have some symmetries, but it is not clear how to write down a nice bound for general polynomial that you get the exact dependence on AR. So in general, you will get pet bounds that depend on R. And if you put them back, like we did here, then you just interchange the averages, and then you have to use a special case of our main theorem to essentially throw away the terms that contain the variable R. And you will, at the end, arrive at similar expressions like this, like iterated limits of polynomial averages. So I skipped many steps here. So this was actually very important, what kind of coefficients you get, because that causes many problems. But let's just stop here, and thank you very much.